Alright, next we'll see how we can train on Native Link Cloud. As always, we'll begin by copying the code. Copy. This would go in training model. And then the script to run it. Awesome, so let me walk you through what's happening. First, we load all of our Hugging Face stuff. We have this utility function that measures the performance of a model. One thing to note is that this function is tailored to the output shape of the model we use for this demo. If you are using a different model, you would most probably have to change how the outputs and the predictions are calculated, and that would be somewhere around here. Alright, this is the main thing here, is the train classifier function. By default, we work with the Prujwal one but tiny. It's a very tiny 4.4 million parameter model, roughly about 17 MB, and we will be fine-tuning it on the sentiment analysis subset of the GLUE dataset. These are the training parameters. Hugging Face has its own cache library, which is here. We just use that, but again, you can obviously choose your own output directory. And then we create the model directory, and then within the model directory there will be a checkpoint subdirectory that will have all of the model checkpoints in case you see better performance at a checkpoint instead of the final trained model. We load the dataset. For a quicker demo, we will only be working with the first half of the dataset. This would be about 33,000 entries, but obviously it's better if you train it on the complete dataset, and then we will reserve the last 1,000 entries of the training set for testing. Cool, we then load the tokenizer, we load the basic model, we tokenize the dataset right here, and then we set up the training arguments. Then we set up the trainer object, and then we actually print out the model performance before fine-tuning, and then we start the clock to measure how long it takes to train the model. We actually commence the training, we stop the clock, and then we print out how long did it take the model to train, and then we also print out how many total parameters and trainable parameters were there. And lastly, we provide two things. First, we just provide a sample inference on just one output just to make sure that the model is working, and we save the model, and then we also test the model after fine-tuning and print the results of that performance. Cool. Instead of showing you how to run this test or this file, which you can do by pasting either of these commands, I want to move on to the cache manager that we've come up with, and we'll show both of these files work in tandem. So one of the best things is that you can cache model weights remotely. So let's start by copying all of the code. So we have the cache manager, and then we have the script for the cache manager. And then lastly, the build file for the cache manager. Alright, let me walk you through what's happening in the cache manager now. First, during initialization, if you have a particular cache directory that you or your organization uses, you can specify that, but by default, at least for this demo, is the same as the default Hugging Face caching library. And then for this demo, for any model that we train or fine-tune ourselves, we generate its own cache hash to save it, and that cache hash is basically just the model name combined with its version or revision, and just generate the cache hash like this, and that becomes the path in the cache where the model is saved. If we train and fine-tune a model ourselves and we have our own custom ways to save, they would be saved at the path described here, and which is why we just check if that directory exists when it comes to retrieving the model. But Hugging Face has its own ultra optimized caching mechanism, and they make it very simple to check if a model has been cached, and you just check the model name in this directory by adjusting the model name based on this format. So you add a model / prefix, and then you replace all forward slashes in the model name with double dashes. And then when it comes to load model, we first check if the model exists. If it doesn't exist, we train it and fine-tune it using the train classifier described here, save it, and then return that model. So load model is guaranteed to always return a valid model and a tokenizer. Now, when it comes to seeing how the cache manager works in its main, again, as I said earlier, that we're working with Prajbul1 but tiny, we create the instance, and then we actually show you both how the cache manager performs with a Hugging Face model as well as a manually fine-tuned model. So with the first one, with the Hugging Face model, unless you've used this model in this particular environment before, you will not have this model cache. So I'm expecting a false here, which would in turn trigger remote environment to download the model from Hugging Face. So this should take time. And again, we measure all of this time performance. And then when we try to reuse that model, now that the model is in our cache, this should be quick. And we'll see the time taken for this part. And just to make sure that we're actually working with the same model, we have this very simple test that matches each parameter with another parameter. So it mostly compares the total number of parameters, but this is a trivial check to see whether we're working with the same model architecture or not. Moving on, we show you how the cache manager performs with a model that we ourselves fine-tune. So because we are not just using a Hugging Face model right off the bat, we first get its cache path, again with the cache hash, and we check whether it's been cached manually. If not, load the model, fine-tune it again on half the SST2 subset of Glue dataset, and then load it, because that train classifier function automatically saves it to the specified output directory. This loading should take a long time because we're also training the model, then saving it, then retrieving it. But then in the second run with this manually fine-tuned model, this should be very quick. And then we are at the end, we also compare whether all of the parameters match or not. So let's see how it performs. We go back to the blog, and then we just copy this, paste, and we're off. This will take a long time, so I'm going to pause it and I'm going to come back when we have the results ready. Awesome. This took about 2 minutes and 15 seconds to run, and let's have a look at the results. I know there are a lot of logs. Sweet. So first we see what the cache directory has been set to. Then we have the first run with a Hugging Face model out of the box, and nope, it's not in our environment, and it took about 1.3 seconds to load. This is already really quick because on my N1 Pro Mac, when I load a model locally, this takes about 11 to 12 seconds. And of course, when you load it from the cache in the second run, it's half a second. Sometimes I've seen it be as low as 0.3 seconds or even 0.2 seconds. Moving on then, with the manually trained model, first we see that nope, it's not in the cache. And then we try to load the bare minimum model that we will fine tune. This is the model performance before fine tuning. It's 44% accurate, and this means that the model performs even worse than random guessing, because random guessing would give you 50% accuracy. And all of these are pretty dire metrics, which is expected. Now we train the model. The model took about 120 seconds to train, so this is just about 2 minutes of training, not even on GPUs. This is just native link cloud CPUs. And right off the bat, we see that the accuracy has gone up to 88.7%. For a very tiny 4.4 million parameter, these are good numbers. Especially that this given that this training took only 2 minutes. And then when we do a second run with this manually trained model, it's already found in the cache, and instead of 2 minutes, it takes 0.03 seconds to load. And yeah, that wraps up the cache manager.